the best estimate of the standard deviation of the data turns out not to be the standard deviation, but it's pretty close. So if we compute the standard deviation, it's 33.3. This is going to be, and we ended up at 35. 33.3. So although this is more like the maximum likelihood estimate, and the best unbiased estimate is a little different. But if I give it my best estimates here, it does a pretty good job. You know, I get a similar cumulative distribution for both of them. I get a mean that looks like it's in the middle. And I did this not by eyeballing it, but just by computing something from the data. And so from now to the rest of the semester, that's what we're going to be doing. We're going to be looking at data, computing functions on it that tell us complex things about it, that help us estimate what's going on in the big distribution. So, and many times there's going to be two different stages. There's going to be the stage of estimation, which might be a really simple thing, or might be something that's packaged away. And then there's going to be the inference that happens after that, about how confident are we about the ranges of values. So I think I'll stop here, and I'll send you this text file so you could work through it again on your own. But that's basically, you know, the basics of inferential statistics. So we have data, we have a model of the data that's usually some type of distribution, and the first step is to estimate the parameters of the distribution that match our data. And although we could do it by hand, by eyeballing it, once we know what we mean by this is a good estimate, which we've talked about a couple aspects of what we mean, then there are sometimes ways to do that directly rather than adjusting it by hand. And in the case of the normal, the way to estimate the mean parameter of the normal from your data is to take the mean of your data. That shouldn't be surprising to you. And the way of estimating the standard deviation is actually the sample standard deviation formula, which is not the standard deviation of your data, it's your standard deviation scale a little bit, and we'll go through next time an example of that. It turns out that the standard deviation of your data is a biased estimate of the standard deviation of the distribution it came from. And if you just use that, you're going to underestimate the actual standard deviation of your data. So that needs to be adjusted for.
You're going to underestimate it?
So you have to scale it a little bit.
I would think it'd be overestimated. Maybe not.
Nope. Turns out it's underestimated. If you generate 10 numbers from a normal distribution, and with standard deviation 1, and compute the standard deviation of those 10 numbers, their standard deviation will average 0.95. Sometimes it'll be greater than 1, sometimes it'll be less. But if you do that over and over again, the average standard deviation of that will be 0.95, because it's a biased estimate of that value. It's systematically biased and we can correct for it. So I'll be eagerly awaiting your tests.
Can we please go over problem 3 and what you're looking for? Steven's explained this like twice to me already,
Okay. You have the data. I've already given you the data. I want you to say plot combo, basically subject 222 or whatever the subject code was, session 1, and then plot, select out that subset of data. If that combination turns out to produce no results, like if I ask for a subject that doesn't exist, you should do something sensible. And then plot response time by trial number for that session there. So I've got, you know, a set of, I forget how many trials are in each session, but maybe there's 50. So I want you to plot response time by across the trial. So maybe it was getting faster throughout the trial, throughout the session. Make titles for that based on subject session. So that is no different than what we did about 3 other times. Then they're really up to 12 sessions per subject, but sometimes, most of them did 8 sessions, so.
So you mean sessions instead of blocks, the first 8 blocks of each participant?
Blocks are 8, sessions are 21, or the other way? Period of plot, response time.
Yeah, so go over the first 8 sessions. Session, I think session and block, there's a variable block in there that it's, I think, it's labeled differently, but I don't think it's any different than session. So go over 8 sessions of an experiment and plot it on a page. You could do something like this, or you know, if you did a PAR to give you a grid of, that's 4 by 2. That gives me, you know, subject 3, session 1, 2, 3. But you'd want to do it for 8. So what I want to be able to see is 8 sessions for a subject.
For each section.
Yeah. And then give me 8 sessions for the next subject. And 8 sessions for the next subject. So none of this is stuff that you haven't done already in the previous homework.